Welcome to Smith's Interconnect 360 Connectivity Podcast. Join our experts as they explore high-end and cutting-edge topics that shape and influence the connectivity world. Enjoy this week's episode.
Welcome to Smith's Interconnect 360 Connectivity Podcast, the podcast that explores the connectivity trends and applications of today's manufacturing sector. I'm Mark Kennedy, Product Marketing Manager, Fiber Optics and RF Components, and I will be your host for today. In this episode, we'll be diving into understanding the performance aspect of different filter topologies. I have with me today Mike Schweyer, Product Line Manager for RF Filters. Hey, Mike, how's it going today?
Hey, Mark. Happy to be here.
All right, let's jump right into them, Mike. Why are RF filters an important component in supporting many space, defense, and aerospace applications?
RF filters are an important component in hardware to support many applications, such as communications, data transfers, and remote sensing. In our technical world, there are many RF signals being transmitted and received around the world.
All right, so RF and microwave filters are very important to ensure the correct data is extracted for each application.
Yes. Also, with all the applications that require wireless communications, a wide array of RF filter topologies are available to obtain the desired information. There are also many considerations for choosing the correct filter type for applications. The most common elements to consider when choosing the RF filter technology are determined in two categories. The electrical performance of the filter consists of three main areas: the center frequency, the bandwidth, and the insertion loss of the filter. Other requirements are based on the application, such as size, weight, and power, or swap, the cost, and the reliability. Choosing the correct filter topology is a critical step in designing an optimal system.
All right. You mentioned center frequency. Can you elaborate?
Sure. The center frequency is determined by the wavelength of the signal, and they are inversely proportional to each other. Higher frequencies generally provide more data capabilities, but can only be transmitted over shorter distances in air, as higher frequencies experience higher attenuation. The low frequencies are used for transmitting signals over very long distances, miles, and may be limited to line-of-sight limitations due to the curvature of the Earth for very low frequencies.
Okay, so you're telling me, Mike, television and radio are good examples of low frequency?
Yeah, Mark, that's very good. Both radio and television are low frequencies used to transmit data over long distances and are in the VHF and UHF bands for up to about 1 gigahertz.
All right. So not being an expert in the RF filter world, what would be considered an example of high frequency?
Oh, well, there are many examples, but one of the common ones now is 5G. They're high frequencies that transmit over much shorter distances, but they can also transfer much higher amounts of data. The 5G frequencies have high bands of up to 40 gigahertz. So based on the frequency of operation, filter topologies emerge as supporting technologies. For example, one common topology for VHF bands are the discrete or lumped element designs, which use inductor and capacitor elements to create the resonant elements of the RF filter design. These filters support frequencies from DC to about 10 gigahertz.
All right. Are there other types of filter topologies in this band?
Yeah, the ceramic resonator filter designs are also ideally used to support UHF up to the middle of C-band, or about 400 megahertz to about 6 gigahertz. And then for higher frequencies, cavity and waveguide filters are available from about 500 megahertz to E-band or even millimeter wave frequencies that extend above 100 gigahertz. There are other topologies included printed filters from L-band into the V-band, saw ball filters for VHF to C-band, and others. But clearly, the frequency of operation for the filter is a good indicator of the preferred topology.
All right, Mike, I'd like to take a moment here just to recap a lot of information you just gave us. So you're saying higher frequencies can transmit more data than lower frequencies, but doesn't also the bandwidth determine the amount of data that can be transmitted?
Yeah, Mark. The fractional bandwidth within the band is also an important consideration for data transmission. For example, both ceramic and discrete designs are available in the L band of 1 to 2 gigahertz. However, if the fractional bandwidth is greater than 30%, the discrete topology would be the better choice. For bandpass filters, the fractional bandwidth is defined as the passband of the filter, the stop frequency minus the start frequency, divided by the center frequency. Some topologies are much better suited to support narrowband filter designs, and others are optimal for wideband.
All right. Earlier, Mike, you addressed insertion loss, which I like to probably jump into that topic, which is power loss through the filter. How would that affect filter selection?
Well, for an ideal filter, there would be no loss within the passband. But of course, physically, this is not possible. Different topologies do offer different capabilities with relation to the insertion loss. Generally, the factor that determines the insertion loss is strongly correlated with the filter's Q or quality factor. This is the ratio of stored energy versus dissipated energy within the resonance structure of the filter. Higher Qs have less energy dissipated and can provide lower insertion loss. Topologies with the highest Qs are the waveguide and coaxial cavity mode filters. This topology allows for the transverse electromechanical or TEM mode to be confined within a conductive material with very low resistive losses, such as silver. The higher Q designs could also handle higher power, as any resistive losses in the filter is dissipated as heat, and less heat allows for higher power handling.
Okay, so why would some choose a higher loss filter?
Some of the benefits would be a smaller footprint or a reduced cost.
Oh, those are definitely great benefits. And you actually brought to the next topic. Can you elaborate on size?
Well, reducing size is important for many applications, but like with most other aspects, there are trade-offs. The amount of power that a filter needs to handle is inversely proportional to the size. That is, the more power handling required, the larger the filter. The frequency of operation, on the other hand, is generally proportional to the size of the filter. As the operation frequency increases, the size of the filter decreases. Finally, the selectivity of the filter does correlate quite strongly with the overall size. The selectivity is how quickly the filter transitions from the passband to the stop band. The more selective a filter is, the more resonance sections are required, and therefore the larger the filter becomes.
Okay, so essentially there are trade-offs across the board. So to get smaller size filter, you must understand that you might have to sacrifice in other areas. I understand.
Yeah, that's right. There's always trade-offs.
Yeah. All right. Are there any other factors individuals should consider when selecting an RF filter solution?
Well, I mentioned considerations that were based on the performance of the filter, and those are typically the most important aspects. Is it physically possible to achieve the desired results with certain topologies? However, environmental considerations also promote certain topologies. Examples of environmental considerations include the operating temperature, shock and vibration, humidity, altitude, and corrosion. There are many techniques to mitigate the environmental impact to the filter, but some topologies are naturally better suited.
All right. Can you give me an example of one?
Sure. Choosing the topology for a filter design can be subjective, as the design techniques has some artistry. Differences design topologies can offer similarities with the product, and small differences in performance or size might not be a critical aspect for the application. Ideally, I believe an important step when starting to review a filter requirement is to prioritize the different aspects of the filter requirements. An L-band application where potential interference from the GPS L1 frequencies would greatly diminish the system would have a top priority of perhaps 40 dB of rejection from 1565 to 1585 megahertz, as an example. Then perhaps loss would be next, as long range is required at the operating frequency. Finally, small size might be nice, but may not be critical as it is on ground-based equipment. Now, depending on how close the operating frequency is to the GPS L1 band, the filter topology comes into better focus. With still a lot of choices, but the low loss requirement probably means a higher Q design, such as ceramic resonator or coaxial waveguide. Most commonly, the projected filter response will be provided in S parameters, and the overall system performance can be evaluated with all the options.
All right, Mike. So let's summarize today's discussion. There are many requirements an individual should consider when choosing an RF filter. But what I'm understanding from our conversation today is frequency, insertion loss, and swaps, size, weight, and power are your three most critical requirements.
Yes, Mark, that's generally the cases. Those are the three most critical.
Thank you, Mike. And thanks for joining, and for your time today, Mike. Your insight around the performance aspect of different topologies was greatly appreciative.
Well, thanks, Mark. I appreciate being here, and thanks for the invite.
That's all for this week's episode of Smith's Interconnect 360 Connectivity Podcast. We hope you enjoyed it and learned something new. If you have any questions or feedback, please feel free to reach out to us through the form in our podcast webpage. Stay tuned for the next episodes in which we'll explore more topics related to connectivity solutions. Thank you for listening and have a great day.